Hello, and welcome to lesson 9 of this Introduction to Linear Algebra with Wolfram U. The topic of this lesson is matrix operations. So let's begin with a brief overview of the lesson. In this lesson, we'll talk about a few important operations on matrices, and those are called addition, scalar multiplication, transpose, and matrix multiplication. Now, just to give an idea of what's going to happen over here, let's say you've got two matrices A and B, like I've defined over here. Then, if you find A plus B, the answer is just the sums of the corresponding entries of A and B. So 1 plus 2 is 3, 3 plus 6 is 9, etc. So that's the sum. Pretty simple. But if I say do 5 times A, then you simply multiply each element of A, each entry of A by 5, and you get back 5, 15, 10, and 35. But if I said do the transpose of A, then all you do is you interchange the rows and columns of A. So the first row of A now becomes the first column of its transpose, etc. And the only really different operation over here, the very difficult one over here, is the dot product, the product of two matrices, and that's given over here as 26, 9, 16, 19. So for example, the 26 over here comes from the following. You take the first row of A and take the first column of B, and imagine placing that first row onto the first column. So 1 times 2 is 2, 3 times 8 is 24. If you add them up, you get 26, etc. So those are the 4 operations for this lesson, and let's begin formally with matrix addition. So let's say you have a pair of matrices A and B, both are m by n, then their sum is denoted by A plus B. Now this sum is also an m by n matrix, and the entries of A plus B are obtained by adding the corresponding entries of A and B. So for example, here are two matrices A and B. Let's check that they've got the same size, and they do. And then you work out the sum. And for example, 9 over here comes from adding the 5 and the 4 over there, etc. So matrix addition is rather simple, and now we go on to scalar multiplication. So let's say you have a matrix A and a scalar C. So C is a scalar, it's a number. Then you can multiply the matrix A by the scalar C, and this answer is denoted by C times A. So for example, here's the matrix A. If you do 4 times A, you are simply multiplying each element of A by 4, so you get 44, 4, 16, etc. But if I do negative of A, then you simply change the signs of all the elements of A. But of course, you could do a large multiple of A, and then you get back the answer quite quickly. Okay, so just some properties of addition and scalar multiplication. So let A and B be a pair of m by n matrices, and let 0 denote the m by n matrix whose entries are all 0. And you've got some scalars C and D. Then the addition and scalar multiplication have got some properties. So for example, if you do A plus B, that's the same as B plus A. If you do A plus B plus C, in whatever order, you get the same answer. If you add the 0 matrix to A, you get back the same result. And of course, you can kind of distribute the scalar multiplication over addition. So C times A plus B is CA plus CB. And you can do the reverse, and you can do C plus D times A is CA plus DA. So addition and scalar multiplication over here are very similar to what you'd see for numbers and not just matrices. Okay, so now we go on to the second operation, which is transpose. So given a matrix A, the transpose of A is obtained by taking the columns of A as the rows of A transpose, etc. So basically you interchange the rows and columns of A and you get the transpose. So for example, here's the matrix A. Its dimensions are 2 and 3. the 2 rows, 3 columns. If you do the transpose, then you simply are interchanging the rows and columns. So the first row now becomes the first column. And of course, the dimensions are now just the opposite. So you have a 3 by 2 matrix. So transpose of a 2 by 3 matrix is a 3 by 2 matrix. Okay, so some properties of transpose. So if you're given a matrix A and a matrix B and C is a scalar, then the transpose of the transpose gives back the original matrix. That makes sense because you're doing transpose twice, so you get back to where you started from. Now, whether you do addition first and then transpose, or you do transpose first and the addition, you get back just the same result. And of course, scalar multiplication can either be done before or after. Okay, so as an example, here is a matrix A. Let's check that if we do the transpose twice, you get back to where you start from. If we take another matrix B and do the transpose of A plus B, that's the same as transpose A plus transpose B. And that's clear over here, but let's check it formally and do get back true over here. Okay, so on to the most difficult operation for the lesson, that's matrix multiplication. So let's say you have a matrix A which is m by n and B is n by p. So you've got the same number of columns over here as the rows over there. Then the product of A and B is denoted by A times B or A dot B. Now how do you do it? Well, you simply take the dot product of the ith row of A and the jth column of B. By which I mean you simply place the ith row of A on the jth column of B, etc., and then you multiply. So the point is that the matrix product is defined only if the number of columns of A is equal to the number of rows of B. So over here, the n and the n should be just the same. So as an example, let's say you have the matrix A over here, the matrix B over there. A is a 3 by 2 matrix, B is a 2 by 2 matrix. So their product is given over here. So for example, the 11 comes from doing 2 times 1 and then 3 times 3, and then adding them so you get 11, etc. And the dimensions of the product are 3 and 2. Okay, now notice over here that if you try and do B dot A, then you get a complaint, a message that says that these do not have compatible shapes. So this message says that you cannot find the product in this case. Okay, so the properties of multiplication are kind of easy. So first of all, we're going to assume that you have the appropriate dimensions everywhere for things to be defined. So what are the properties? Well, if you do A times BC, that's the same as AB times C. If you do A times B plus C, that's the same as AB plus AC. If you do B plus C times A, that's the same as BA plus CA. And you can do the scalar multiplication either first or here or there. But the key point is that in general, you do not have A times B equal to B times A, even if the matrices have the correct dimensions. And one last thing is that if you do AB transpose, that's same as B transpose A transpose, because it's like reversing operations which don't commute. So basically you reverse the second operation first. Okay, so as an example for all that, here is a matrix A, here's a matrix B. Let's check that if you do A dot B and if you do B dot A, you do not get the same result. So matrix multiplication is not commutative. So A dot B is not the same as B dot A. And then if you do transpose of A dot B, that's the reverse product of the transposes. So you do transpose B dot transpose A to get back the same result. Okay, so that's the end of this lesson. And the main point is that you can do several arithmetic like addition and structural operations like transpose on matrices. Now, in this lesson, we talked about addition
scalar multiplication, transpose, and matrix multiplication, but of course there are many more that can be done. And the key point is that matrix multiplication is not a commutative operation. So you cannot assume that you can interchange A and B. And having done this, the next lesson will talk about the inverse of a matrix. But for now, I'll stop over here. Do review this lesson, and I'll see you in the next lesson. Thank you. I'll stop over here.